Okay, so this is section 4.1, the start of chapter 4. We're actually going to be getting into integration in this chapter. Just like everything else, though, we've got to build some background as to some things before we can actually get into kind of the core here. So what we're going to start talking about first is the idea of areas and distances and how they kind of correspond. And we're going to talk about some things which are um, I would hope that they're relatively basic at this point, things that you probably heard before. So first thing we're going to do is we're going to approximate the area under the curve and the distance traveled. Okay, we're going to kind of see how those things fit together. An area under the curve, I'm going to have to qualify and say it's actually the area between the curve and the x-axis. So typically we say area under the curve, but really what we mean is the area between the curve and the x-axis. All right, example 1. If a constant rate of 30 miles per hour is obtained for 10 hours, how far has the person traveled? And how did you determine your answer? Hopefully that's not that difficult. If you've traveled 30 miles per hour for 10 hours, seems to me like you've gone 300 miles. And how would you get that? Well, you'd multiply 10 hours. You've traveled for 10 hours at 30 miles per hour. If you go 30 miles in 1 hour, you're going to go 300 miles in 10 hours by multiplying. So you would get 30 times 10. You would get 300 miles. And where does that come from? It comes from a really basic scientific unit that distance equals rate times time. Okay, it's probably something that you've heard before. Distance equals rate times time. Okay, so let's take a look at it graphically. If we've traveled 30 miles per hour, we're going to label this as our 30 miles per hour. And we've traveled for 10 hours, so along the x-axis here, we're going to say that this is t equals 10. Well, if you kind of look at what we've got here, and you were to take the area of that rectangle, area in here of that rectangle, well, area of a rectangle is base times height, so 10 times 30, 300. That's all that it is. It's the area of that rectangle. Okay, so you can kind of see how the area between that curve, which is the y equals 30 line, and the x-axis, which is a 300 area, corresponds to the distance being the rate times the time of 300 miles. Okay, not too difficult, but we know rate is not always constant. Okay, obviously we don't typically hold a 30 miles per hour for 10 straight hours. That's not usually going to happen. What if instead we start off with the fact that the rate might start at 0 because we're starting, before we start or something like that. And then maybe we only get up to 20 miles per hour this time. So this might be 10, that might be 20. And in 10 hours, down here, we only get up to 20 miles per hour. Well, it's the same concept. If I were to take and find this area, I could very easily figure out how far we've gone. Well, this is obviously not a rectangle, it's a triangle. So we need to know that the area of a triangle is 1/2 the base times the height, or the area here is going to be 1/2 of 10 times the height, which is 20 of your triangle. So 1/2 of 10 is 5 times 20 is 100 miles. And that's assuming that we started at 0 as far as miles per hour, finished at 20. And obviously we had a constant rate there of increase up to 20 miles per hour by the time we hit the 10-hour mark. So didn't go very far, obviously, in those 10 hours, but that's what you would get. All right. What if we don't start looking at where what we, where we traveled until we've already gotten up to at least some speed. So maybe we've already gotten up to 10 miles an hour by the time we start looking, and then that would be 20 and that would be 30. So maybe we finish at 30 miles per hour, but once again, we're going to say that this is over a 10-hour period. Same exact principle. We're going to find the area of this geometric shape. And there are different ways that you could go about doing this. You could split this into a triangle and a rectangle if you wanted to. You could say, okay, I've got a triangle on the top and I've got a rectangle on the bottom. That is one way to do it. Not the way I'm going to choose to do it, because if you haven't already recognized, this is the area of a trapezoid. Now, the area of a trapezoid is not typically something that we all memorize, but it's really not that difficult to do. So the area of a trapezoid, I'm going to write this down for you. The area of a trapezoid is 1/2 the sum of the two bases times the height. Now, it's important that we label some of this because not everybody always remembers. Everybody thinks of the base as being the bottom. In the case of a trapezoid, the bases are the parallel sides. So in this case, I'll use orange for this. In this case, this piece over here is a base, while this piece over here is a base. Those two sides are parallel to each other. Okay, the perpendicular between the two bases, this is perpendicular between the two bases, that's considered the height. So in this case, the height is actually along the axis where the two bases are vertical. The angled line there is not either, it's not either one. It's not the height or the base, because we don't measure a height diagonally, and the bases have to be parallel. So here's something else to kind of help you remember this. If you were to take and make one of the bases, like let's say that we make B1 0. So if base 1 is 0, really what that would mean is there would be no distance here. So if we make base 1 0, the distance would actually be like right here would be B1. It would come straight across like that. And then if you just look at what you have, if B1 is 0, the upper part is just a triangle. Well, think about that. If I take and I make B1 0, that goes away. All you have left is 1/2 base times height. That's a triangle. So really, if you think about it, a triangle is a trapezoid. Think about that. A triangle is a trapezoid where one of the bases is 0. So if you know the area, if you know how to find the area of a triangle, which most of us know, 1/2 base times height, you know how to find the area of a trapezoid. It's just a second base added in. So there you go. There's your little way to try and remember how to find the area of a trapezoid. So in this case, now we can go ahead and finish this. Our area is going to be 1/2 the sum of the bases. The first base is 10. The second base is 30. And then the height, remember, is along the x-axis in this case, or the t-axis, and that would be 10. So our area is going to be 1/2 of 40 times 10. 1/2 of 40 is 20, times 10 is 200. So we would have traveled 200 miles. And obviously, these are not terribly difficult as long as we know these basic geometric shapes. This is going to be a little bit more challenging. How would you determine the distance? Okay, area of a trapezoid. And I suggest knowing how to find the area of a trapezoid because we are going to be using this throughout this section and throughout the chapter. But again, this is easy to do, or relatively easy to do, because these are all geometric shapes that are very simple for us to find areas of as long as you know the formula. What if, however, we have something like y equals x squared, and we want to know the distance traveled between 0 and 4? Y equals x squared is clearly not a regular geometric shape that we know the area of. So if we were kind of to sketch y equals x squared between 0 and 4, so let's say this is 5, 10, 15 for our height, and I'm going to do my best here to make these evenly spaced. 1, 2, 3, 4. Probably about as good as I'm going to get. So that would be time 1, 2, 3, 4. So we are trying to find the distance traveled between 0 and 4. So let's plot some points. At 0, the rate would be 0. That's plugging into x squared, by the way. Plug 0 into x squared. Plug in 1, you're going to get 1. Plug in 2, you're going to get 4. Plug in 3, we're going to get 9. Plug in 4, we're going to get 16. So clearly you can see that that's not a regular geometric shape as far as like being linear pieces or something like that. It's going to look something like that. There is your parabola from 0 to 4. Good thing I don't have to do that again. I probably couldn't do it that well. So the idea is, I don't know how to find the area easily. Well, that's not true. I do. But there is no geometry way of doing this. There's no easy geometric shape way of doing it. What we can do, however, is we can approximate. And that's what it says right there. We can approximate the total distance traveled. Now, there's several ways to approximate. So we're going to kind of walk through these slowly if possible. One way is to use rectangles. Actually, the first 3 ways are all going to be using the idea of rectangles. The 4th way will be using trapezoids. We'll kind of resketch the drawing at that point because it'll get too messy. But I can use rectangles. So as long as I know a base and I know a height of the rectangle, I can find the area of a rectangle. So the first thing that I'm going to do is I'm going to say, okay, what if I take the right-hand endpoint or the right upper corner of my rectangle to be on the graph? So what do I mean by that? The right upper corner of the rectangle. So I'm going to create a rectangle. That's the right upper corner. So if I were to draw a line straight down, that's the right side. I'm going to have to draw the rectangle. I'm going to draw it over to the next dot and then bring it down. So there's one rectangle. Again, the right upper corner of the rectangle hits the curve. So then I'm going to draw another rectangle. Once again, I'm going to make it start at the current rectangle. I'm going to say, okay, the right upper corner, starting at where x is 3, is the upper part of my rectangle, and then I'm going to draw another rectangle. The right upper corner has to hit the curve, so it's going to hit there, and then over and down, and then the right upper corner will create the last rectangle, because now we've got from 0 to 4. This is what is known as a right-hand endpoint, or right Riemann sum approximation. I'll explain what all that is in a second. Excuse me. So you could see this written in a lot of different ways. I think it's a right R-RAM or RR-RAM or something like that, right Riemann approximation method. In any case, it's a right-hand endpoint approximation method. That's what we have here. If you look at what's in green there, I can easily figure out what the areas of those rectangles are. Each one of them has a base of 1, and the height is going to be determined by that upper right-hand corner. That's the important part. So let's see, if I wrote all this out, I would have the first rectangle has a base of 1 and a height of 1, so 1 times 1. Plus, the second one has a base of 1 and a height of 4. The third one has a base of 1 and a height of 9. And the last one has a base of 1 and a height of 16. So I can clearly add all those things up. I'm going to get 1 plus 4, which is 5, plus 9, which is 14, plus 16, which is 30. So you'd have an area of 30 units squared, whatever the units would happen to be there. I can use that method. I can also do it the other direction. Let's say that we want to let the left-hand portion of the rectangle, the upper left-hand corner of the rectangle, be the part that hits the curve. So I kind of start on the right. I'm going to start on the right-hand side here. I don't have to, but I'm not going to put a dot right here because there's no place to go that direction to create another rectangle, since 4 is the end of my domain. So I'm going to start here. Now this time, this is the upper left-hand part of my rectangle. Well, if it's the upper left-hand part, then that means I have to create a rectangle which goes to the right and then down. It's supposed to be at the 4. I kind of missed. And then this piece right here would come down, just like I did before. Now the upper left-hand part is going to create the next rectangle. So from here over, and then down, and then down. It's supposed to be on the same line. I'm just trying not to cover my lines. And then here, over, and down. And then the interesting one is this last one. If I start here, there's no place to go down. I'm just going to go over because I'm already at the bottom there. But now you can see how I have 4 rectangles in that case. This is what is called the left Riemann sum, or the left-hand endpoints, because the upper left-hand corner of the rectangle hits the curve. So once again, I can do a base times height for each one of those rectangles. So for the first one, I'm going to have to scroll back up and down. For the first one, the base is 1, but the height is 0. I've got no height. It's just a straight line. The second one, the base is 1. The height is now 1. And so on. So hopefully you can look at your graph while you're doing this. So the first one is going to be a base of 1, height of 0. Base of 1, height of 1. Base of 1, height of 4. Base of 1, height of 9. And that's the last one that I have here. Base of 1, height of 9, because I can't go any further to the right past 4. So let's add all those up. So I'm going to get 0 plus 1 plus 4 is 5, plus 9 more is 14. Now, you've probably already figured this part out. It is pretty clear that with the right-hand rectangles, in this case, because it's not always the case, but in this case, the right-hand ones, which were the green ones, I've got all of this space up here, which is clearly not underneath of the curve. So I've got a bunch of space here, which is over accounted for. So that first approximation is going to clearly be an over approximation. With the red rectangles, I've got all of this space right here, which is clearly not accounted for because there's still space under the under the curve that's above the rectangle that I just haven't accounted for. So all of the stuff for our left-hand approximation is going to be an under approximation. Those rectangles under approximate the curve. Well, there's one more way that we could do this, and it'll give us a much better approximation. We can use what's called the midpoints. And that's on the next page, but I'm still going to show it here. So the midpoints. The idea behind the midpoint is we are going to take the middle x value in between all of these to find the height of the rectangle. Now the base is going to stay the same. This right here is still the base. I'm just going to take the middle of the base to find the height. So the bases are all still 1. But if I use the middle of this base, basically if I were to use like 3.5, I'm going to go 3.5 all the way up to the curve, and that's where it's going to hit the curve. And then I'm going to put a line across, and then we're going to come down. Same idea. So at 2.5, I'm going to go ahead and put a dot there in the middle, and then we're going to draw a rectangle. Again, these are supposed to go all the way up against the edge. I'm just trying not to cover up all the colored lines here. And hopefully what you can see by doing that is that now with this one, like let's look at the one on the right, I've got some space up here, which is over accounted for, and then I've got some space up here, which is under accounted for. It's going to be very close in this particular curve because it's y equals x squared. It's going to be very close to being a very strong approximation because of the fact that the amount over and the amount under accounted for are very close to each other. They're not exact, obviously, but they are close. So this is what's called the midpoint approximation. Now, to use the midpoint approximation, again, the bases are the same. The difference between 0 to 1, 1 to 2, 2 to 3, and 3 to 4, those are your bases. Those are the same. It's the heights that changed. And I'm going to use the middle in between 3 and 4, so 3.5, in between 2 and 3, 2.5, and so on, to find the heights of the rectangle. Well, you might ask yourself, well, how am I going to do that? Because those points weren't on the original graph. Well, they are. Just have to go back up to the original function and plug in 0.5, 1.5, 2.5, and 3.5 to figure out the x values. So on the next page, we're going to use the midpoints, which is, if I plug in 0.5 into x squared, you get 0.25. If you plug in 1.5, you get 2.25. If you plug in 2.5, you get 6.25. And if you plug in 3.5, you get 12.25. And you might ask yourself, well, why didn't I multiply everything by 1? I will, but that's because whatever the size of the base is, as long as it's the same base all the way across, you can actually pull that out to the front, factor it out, and just multiply it once. Of course, it's 1, so it won't make any difference here. But then if we add all that stuff up, we get 21. All right, we are going to come back in the next video, and we're going to start doing the trapezoid method. But the first 3 are all rectangular methods: left hand, right hand, and midpoints.